Let's begin talking about our sedimentary processes just focused on weathering, because weathering is so important. I want to give it some extra focus. And then in a later sub-lecture, we'll talk about the other processes. But let's talk about weathering a good bit here. First, let's put these processes in order. We start where we break down rock. We weather it, and that can be mechanical or it can be chemical weathering. Mechanical means we're breaking down the rock into smaller pieces, but we're not changing the chemistry, the bonding, the chemical composition. Chemical weathering is things that do change the bonding. That could involve things like dissolving certain minerals, or it could be precipitating certain minerals, or it could be changing the minerals that are there. All of these are chemical changes and are involved in chemical weathering. Later, we'll have erosion and mass wasting, where we move those sediments and get them moving. And then we have transport in some environments past other environments based on the energy of those environments. And then later, those sediments get left behind somewhere, they're deposited. And then processes of compaction and cementation turn those deposited rocks, if they get buried, into new rocks in a general process called lithification. So I said there were two types of weathering. We've got mechanical weathering, that's physical breakdown of rock into smaller pieces without changing its chemical composition. This happens as a result of physical processes, something like frost getting inside in cracks in rocks and breaking those cracks open. That would be physical or mechanical weathering. Chemical weathering involves chemical breakdown, which changes the bonds between chemical elements. We've seen sort of a man-made version of a chemical weathering process when we put acid on a limestone or on calcite. And we saw that it fizzes as the bonds change, as we take one of those carbonates that make up the mineral, and we add some acid to it, which is really just made of H pluses. You don't really need to worry about the chemistry, but if you're curious. And once we do, it turns it into CO2, which is now a gas. We've changed the bonding, plus water. That's a type of chemical weathering that does naturally happen, where the carbonate minerals break down into carbon dioxide and water. And so that would be chemical weathering, because the bonding has changed. Let's talk about some examples of mechanical weathering. Exfoliation. If we take a rock, this is probably like a granite or something, right? So it used to be underground because it's an intrusive rock, so it must have formed inside Earth. And we erode everything that was above it. Now, no longer do you have pressure pushing on that rock. You don't have that confining pressure anymore. And as a result, the whole rock tends to expand just a little bit. You also have these small changes in size because you have sunlight hitting it now, so it heats up, it cools down, it swells, it shrinks just slightly, and over time, that does promote cracking in the rock that can cause the rock to crumble. It's still the same pieces, so it's mechanical weathering. And you can see evidence of it on this rock face here, and you can see the rubble pile left below the surface here, both caused by exfoliation. Changes in size are really what's causing this, and it's either because of loss of confining pressure or it's because of changes in temperature due to heating and cooling, changing the size slightly. Another common one is called frost wedging. So if you had a rock and it was summertime and some joints or cracks existed in the rock and water fills them in, and then seasonally, right, it comes to wintertime and that water freezes. When water freezes, it expands. That's key. It's the physical part of this, right? We're in physical geology. So when water freezes, it expands, and that expansion causes it to exert a force on the rock, and it actually wedges it or pushes it apart. So that's a major part of mechanical weathering in places that are seasonally cold enough for water to freeze. Not going to matter so much in most of the tropics, but in temperate zones like Tennessee, like most of the US, Frost wedging is a key component of mechanical weathering. Let's think about this for a moment. Why is it that water is so effective at breaking rocks apart? We've seen one example already. Is it that its melting point lies halfway between the extreme coldest and hottest temperatures at Earth's surface? Is it that water expands when it solidifies to form a liquid? Or is it that water readily seeps into and fills cracks in rocks? Well, as we saw for frost wedging, all of these three contributed. So a lot of the properties of water are important to how it is so effective at breaking apart rocks. And these are just the mechanical reasons. We'll see that water is really useful for chemically breaking rocks apart too. Here's an example of frost wedging that has happened in Antarctica. It's actually taken the solid boulder, taken small joints that once existed that probably looked more like this one or that one. A little bit of water melts, a little bit of water gets inside, then it very definitely freezes if we're in Antarctica. And it wedges that rock apart over time. And so we see that in a place that the rest of the rock hasn't been transported away, and we can see very clearly how that rock has been frost wedged apart several places. Pretty cool. One major product of frost wedging that you can see as a landscape feature sometime, this word should continue, this is talus slope or scree slope. You'll see it called both, depending on what kind of the world you're in. But these piles of boulders and gravel and rock chunks of various sizes that have formed at the base of mountains are a major product of that frost wedging. So these pieces used to be connected to the rocks up here, but over time, frost wedging has caused those to break apart into chunks. And what do they do then? They fall down slope under the force of gravity and leave a nice big pile here at the bottom for us. So those steep slopes that are covered in gravel on mountainsides, that's what they're a result of generally. Different type of mechanical weathering called glacial polishing occurs underneath glaciers. So these right here, they're just rocks, right? This is a temperate zone. We see plants growing here today. But at some point in Earth's past, a glacier moved apart across this part of Alaska, right? A big ice sheet. And that ice sheet was carrying with it little pebbles, sand grains. And as it brought those very slowly in one of these directions, either this way or that way, hard to tell just from this right here. But as it dragged those particles across these exposed surfaces of rock, it gouged them over time, right? Like nails on a chalkboard. This glacial polishing would have gouged the rock and also worn down the surface of it relatively smooth, which is why it looks kind of shiny in this picture, right? It's like kind of bluish white because it's reflecting the light from the sky just a little bit. It has polished this rock and left gouges in it. So that's glacial polishing. Surprisingly important to mechanical weathering is the action of tree roots. So trees growing down into rock, trying to get at the nutrients and the water that are there. Those roots grow into cracks and crevices that exist in these rocks. And then those roots expand over time, right? The plants are building their bodies out of the carbon that they're gathering from the atmosphere and causing those roots to grow. And because it's exerting a force on this rock, it wedges it apart, pretty similar to frost wedging, except in this case, it's actually caused by plants. When you see trees that look like this, there used to be rocks here, right? They have fallen down and probably made a talus slope below that. The only reason that they're still standing here is because this tree is doing a pretty good job keeping itself alive, and it's gone deep enough underground that these roots continue and are probably wedging apart the rock below as well. Another important one is abrasion by wind. So if you sandblasted a rock for a long time, you would wear down a surface of it pretty smooth. You would polish it a little bit. And you can see that reflected in some rocks that are in the desert that are called these ventifacts. where wind charged with sand sort of sandblasts one side of a rock. And then because the rock rotates or because the wind rotates, you get these surfaces meeting that are kind of curved, they're kind of irregular, and they meet at these sort of, that kind of looks like a seam in the middle of the rock, actually. And that's because wind carrying sand once blasted this side, and at another time blasted that side, and made this rock that we call a vent effect that actually records the direction at which the wind predominantly was moving. So all the weathering we've talked about so far has been mechanical in nature. It takes rocks, it breaks them down into smaller pieces, but it doesn't change any of the chemical makeup of those rocks. In contrast, here, we see some evidence of chemical weathering. What am I talking about? Well, these sediments here, this deep rust red color, comes from the precipitation of iron oxides, like hematite, right, which is Fe2O3, a major component of rust. That involves taking rocks with some iron content in them, changing the way that that iron is bonded to other elements so that it ends up only bonded to oxygen. And what you are left with is basically rust. Rust has covered the surface of these rocks. Let's talk about a couple ways in which that can happen. So water, in addition to being a good mechanical weatherer, is a good chemical weatherer because it can carry away ions from minerals, right? It can dissolve those ions from, say, a feldspar particle, right? Feldspars, which ones were those? We had plagioclase and orthoclase, and they form these prisms, and they have, as part of their mineral structures, some of them have sodium or potassium or calcium in them. And these ions are things that water, if it gets into the cracks in the rock, can actually grab those ions out and start to dissolve them. And that makes a small pit that more water molecules can get into, which makes a larger pit that even more water molecules can get into. So what you see happening here is the rock actually dissolving in these rectangular shapes as more and more of that crystal structure gets eaten into by water. First, it pulls at these ions, and then the rest of the structure can break down around it. And then it goes and pulls at more of those ions. And that's just what dissolution is. It's just taking stuff that was solid and moving it into the aqueous phase, making it so that it's surrounded by water molecules and turning it into ions. As these feldspars dissolve, I want to point out that they tend to form a new type of mineral. They chemically change from a feldspar into dissolved ions as part of it, right? Sodium, potassium, and what we call clay minerals. So those clay minerals are sheet silicates, much like mica, not exactly like mica, but they do form these sheets like you can see diagrammed here, right? This is one sheet here, this is one sheet here, and they extend, in reality, much further than this. They have complex structures, and they usually have microscopic particle sizes. There's no way for us to identify really a hand sample of a clay mineral because they're so microscopic. So that's why we don't really go over them in the mineralogy part of this course. If you zoomed in and looked at them with a microscope, they look a lot like micas though. They have this layered structure to them. It's enough to know that it is a silicate mineral that forms from weathering of feldspars and other silicates. You should also know that clay minerals are a type of mineral, not only a particle size. So that's sometimes gets confusing too. Clay minerals are often clay particle sized, and we use the term clay to refer both to a type of mineral and also to a microscopic particle. Just be on the lookout for that. Chemical weathering tends to work on the edges of rocks and minerals a little bit better because there are more sites for a water molecule to get to access, to start to pull on ions, so that any rough edges do get smoothed out by chemical weathering. And in this picture from Joshua Tree, we can actually tell that some of those rocks have rounded so much that it's produced these spheroids. The spheroidal weathering results with these smooth surfaces from chemical weathering, from breakdown at the sharp edges, occurring as water dissolves things that are there. And here's how that spheroidal weathering is produced. If you have a set of joints in the rock and they sort of intersect each other, joints just being breaks in the rock along which rocks have not moved yet, the water percolates along those and it starts to eat away at those sharp edges, right? And so we start to round the edges a little bit. Like you saw when we were talking about sediments, the longer you spend breaking down an angular sediment, the more and more rounded it's going to get until it leaves behind these things that can basically be spherical in shape. They're certainly very rounded edges. I want to talk about just a little bit of quantitative information here, and talk about the rate of weathering and how it's an example of what we call a positive feedback, which means that once it gets started, it quickly snowballs. What do I mean? So if you took a rock and you started to weather it by breaking it just into pieces, right? You're going to increase the surface area because now you've created more surfaces of that rock. Because you've increased the surface area, there's more area available for chemicals to get into and promote weathering, which increases the surface area even more, which promotes more weathering. So once this process of weathering gets started, it quickly snowballs and accelerates until the rock is totally broken down. That's what I mean by a positive feedback. A change to that feedback amplifies itself over and over again. Right, like audio feedback, that's kind of what it is. A microphone picks up a sound and amplifies it some more, and then it picks it up and then it amplifies it even more until it really hurts at a concert. All right, let's do just a little bit of math to prove to ourselves that as you break up a rock along surfaces, that you will increase its surface area. So let's start by saying that we have a granite cube that measures 2 feet on an edge. What is the surface area of that cube? If you don't remember how to do it, remember that how you calculate area, right? If that's 2 and that's 2 feet, what's the surface area of one face? It's going to be 2 feet times 2 feet gives you 4 square feet. The units change. How many of those faces do we have on a cube? We have the front and the back, we have the top and the bottom, we have the left and the right. We've got 6 faces. So the total area is 24 square feet. Let's take that same cube. Let's split it in half. That way, well, and that way too, right? So we're splitting it in half in all 3 directions. And now we have 8 granite cubes measuring 1 feet on an edge. So 1 foot times 1 foot, that's 1 square foot. 6 faces, so each cube is 6 square feet total. How many cubes? 1, 2, 3, 4, 5, 6, 7, 8 equals 48 square feet. So by breaking up that cube into smaller pieces, we doubled the surface area. Nothing else about the cube has changed. It's still the same volume of granite, still the same mass of granite. Just by breaking it up, we have increased the surface area. And in terms of weathering, that means that it will weather faster once we break it up. There's this process called differential weathering that contributes a lot of what we see in terms of landscapes that are formed on sedimentary rocks. So this one's important. Differential weathering is caused by the variations in compositions of minerals. And it refers to the fact that weathering of different types of rocks made of different minerals happens at different rates. So for example, in this rock outcrop down here, the rock underneath has clearly weathered away faster than the rock above. Right? All of this is breaking down, and we can see it kind of crumbling there. whereas what looks like a sandstone above it is still standing flat, not weathering away very fast. So this contributes not only to things like this cliff face here, but all sorts of the mesas and cliff faces that you see out west, and even a lot of the topography that you see in the east and like Tennessee. The hills that make up a lot of the rock in Tennessee are more resistant to weathering, and the valleys are places that the rocks are less resistant to weathering. Hills tend to be sandstone or a little bit of shale, and the valleys tend to be limestone. We can see that same differential weathering in this igneous or metamorphic rock over here, where this light colors, they stick out more than the dark colors do, probably because the felsic minerals in whatever igneous rock this is stick out more than the mafic minerals underneath. Right? We've switched to talking about igneous rocks, but it's just the weathering that we're talking about. So we haven't even considered forming the sedimentary rocks yet. So we can talk about weathering of igneous or sedimentary or metamorphic rocks, but that weathered material only builds itself up into sedimentary rocks. Just mention that now to say why the terms mafic and felsic just came up. This differential weathering can create some really unusual rock formations like you see here. And like I said, it often explains which rocks forms hills and mountains versus valleys, based on which ones weather the fastest under certain conditions. So I mentioned some of the mesas and buttes that you see out west are because of that. And if I look at this as a geologist, I see these flat-laying layers of rock here, and then like a darker flat-laying rock there that's got some angle to it, right? And flat-laying, an angle to it, and a flat-laying. When I look at this, I say there's probably a package of resistant rock with an R here, resistant rock with an R there, resistant rock with an R there. And then it's this rock in between that has started to break up. Weak rock there, weak rock there. And just guessing out west, this is probably sandstone, more resistant to weathering. And this is probably shale, which is less resistant. More resistant, less resistant. And that's what builds up into these sort of stair-stepped cliffs. The more resistant rocks make up the cliffs, and then the slopes are made of the less resistant rocks that have started to crumble. So here's an image from Bristol, Tennessee. In the Ridge and Valley, which is the province of the Appalachians that we're in eastern Tennessee, we have these long parallel ridges of hills that are probably made of rocks that sort of dip down that way. And there'd be another layer of rock that would have made up the valley where it's still there. And we get another layer of rock there. And that's how you get these parallel ridges of resistant rock and valleys where the less resistant rock is. In Tennessee, this is probably limestone, as I said. And this is probably sandstone, or maybe some shale, or sometimes even dolostone, because dolostone is more resistant than the limestone is. But just how resistant it is depends on the rock. So this rule that I will call Golddich's rule of weathering is that iron-rich minerals tend to weather rapidly, and that silica-rich minerals tend to weather slowly. When we were talking about igneous minerals, right, these were mafic, these were felsic. Since we're talking about weathering, I can use those terms because we haven't turned them into a sedimentary rock yet. If you see a black sand beach, they're pretty rare. You don't see them in the US much unless you go to, what's this? This is Hawaii. You can see them in Iceland too. This sand is made of mafic minerals, right? The hornblende, the olivine, the plagioclase, some augite that all make up these igneous rocks. What was this one? Okay, it's vesicular. It's mostly fine grained. So this one's going to be basalt, right? Because it's dark, it's mafic. So there's a lot of basalt in Hawaii, as we've said before. If that stuff breaks down, originally it will produce sediments, right? Some sand that you might find on a black sand beach. But that's because these minerals just haven't weathered away yet. They're actually weathering away very quickly in the grand scheme of things. It will only take a few thousand years for all these minerals to dissolve almost completely. or to weather to things like clay minerals. So if you see a black sand beach, it's immature, meaning that it hasn't weathered much yet. Which also means that it's relatively young. Whereas white sand beaches are very mature because they're left mostly of quartz at first. Some feldspar and some micas might contribute. This is probably not biotite. This is probably muscovite. Hard to tell from the picture. But as these things weather, right, the mafic minerals weather away first, and you're left with these, and you have sort of your standard beach. And then if you weather these away even more, even the muscovite and the feldspar disappear, and you're left with only quartz. So those really, really bright white sand beaches are sometimes due to the fact that all of the other minerals have weathered away, and you're left with only quartz on the beach. And that's down to their properties. Right? Quartz is more resistant to weathering because it's very silica rich. We go back to that rule. Mafic minerals weather faster than felsic minerals do. That is because of the reactions that iron engages in, right? The iron that's in those minerals, at least in part, it's down to that. Water can promote a chemical change called oxidation. What we have here, what we're showing, is the chemical change that occurs when metal iron rusts. So we start with iron metal, it has nothing else, it's just iron. So we just write it as Fe. We combine it with oxygen, and we create what we know mineralogically as hematite, Fe2O3. It's the formation of rust, too. Rust is sort of microcrystalline versions of this oftentimes, or amorphous versions. But it's all going to be iron oxides and related stuff. This chemical change is essentially what occurs in rocks, except that you're really starting from Fe2 plus in rocks, going to Fe3 plus in rust. But it's the same idea. You're combining it with oxygen and you're undergoing a chemical change. And to avoid scaring too many of you away with more chemistry details, we're going to pretty much leave it at that. But know that if you've got iron in rocks, it can rust, and then it turns that rust red color. That's behind the color of Mars, for example. There's a lot of iron 3+ in different minerals at its surface. It's also part of why we think that there used to be at least transient water on Mars, and why we've always thought that, because a lot of oxidation that occurs during rusting is promoted by water being around. Doesn't have to be, but it often is. We can also see red sands in some places on Earth that are due to that same iron oxidation. Another important chemical weathering process involves the formation of acid rain. Turns out that if you combine CO2 and water, you get what's called carbonic acid. This acid here, it's got a bunch of protons in solution, and that's what makes it an acid. Don't worry about it too much if you're scared of chemistry, but it is this acid that makes rainwater naturally acidic. Turns out that humans can add to that and sort of artificially increase the acid rain, but rainwater is naturally slightly acidic. So that's a starting point to think of. Let me write that down, because it's important to how it affects different rocks. We've seen acid before, right? Because if you take calcite and you add acid to it, what happens? You can dissolve the calcium, you turn that carbonate into CO2, which bubbles, if you have concentrated enough acid anyway, and water. What's happened to your calcite? It is chemically weathered, it is broken down in response to the acid. Acid breaks down carbonates. So that is a common reason that things like limestones weather, because rainwater is naturally acidic, it's naturally going to break down limestone, thus it forming valleys in places like Tennessee. It also contributes a lot to just natural degradation of human-created sculptures. So this used to be a gargoyle or a sculpture on the side of the Roman Forum. Used to be nice and pretty. Now it looks like some horrible eldritch skeleton or something because it's been broken down by natural acid rain. I wanted to point out that a lot of times if you pick up a rock, it will have like different color zones to it, right? Like the outside might look sort of rust red and the inside might be white or black or some other color. The combined effects of oxidation, acid, dissolution, and hydration reactions, all those different things that we talked about, will chemically change the minerals in rock samples. And they do so primarily for the outside in, right? The chemicals can't penetrate to the center unless you break it off. And these surfaces have been broken off, but originally this was just part of, one big rock. From the outside in, those chemical changes happen. From the outside in, they happen there. From the outside in, they happen here. And they create what we call weathering rinds. They look like the rinds of a watermelon or some other melon, right? Where the good stuff, the unweathered stuff is in the center, and the gross stuff, the broken down stuff, is on the outside. Because as water moves through, it affects the outside first. So when you break open a rock, a lot of times you find one of these weathering rinds. And a lot of times that weathering rind will be brownish or reddish in color because of that oxidation of iron that we've already talked about.